So how cells sense oxygen, and of course this is my favorite topic because this is what I work with. Okay, these are the guys, and that is the guy that we talk about, that dude there. So that's Peter Ratcliffe. I'm coming back to him. So they did actually discover this whole system. So that guy lives in the UK. A lovely fella, truly. And these three guys, 2019, they got awarded for what they have done for all of their lives to understand how cells sense oxygen. And this is the work they did. It doesn't look like much, does it? But this is what you get Nobel Prizes for. So how it happens is that you have a cell here in light blue, and you have 21% of oxygen, the normoxic condition. So you have that HIF that I already mentioned, hypoxia inducible factor. But HIF, it's a transcription factor, it's a protein, and when it's kept in oxygen, so you have oxygen as the molecular oxygen, there are these enzymes in cells called prolyl hydroxylase enzymes, and what they want to do is that they want to attach themselves to this moiety, this HIF1 alpha, okay? And as soon as the PSD enzymes do, they hydroxylate proline, they're prolyl hydroxylases, so they hydroxylate proline. I'm not going to go deep into this, other things as well, but it forms a complex. And as soon as this complex forms, this protein, VHL, 1-hippolindyl protein, this is like a red flag for VHL. VHL comes and attaches to this whole thing, and this complex is ready to go for autosomal degradation. Okay? So if you have oxygen, you have the enzymes that target HIF, HIF gets degraded. And all of this, interestingly, it takes about, the half-life of HIF protein is 5 minutes. So this completely, if you work in 21% of oxygen, if your cells are in a BSC or in an incubator, you have no chance, of recovery. Hypoxia, low oxygen. The same thing. You still have the HIF, it's expressed, it's ubiquitously expressed in all cells that we know of. But because there is no oxygen, these enzymes that have high affinity for oxygen, if there is low oxygen, they cannot function because they need molecular oxygen to function. So they cannot earmark, if you may, HIF. Instead, HIF remains intact. It moves to the nucleus, where it has HIF1 beta or ARNT, and they form a dimer. And now this dimer attaches to their hypoxia responsive element, which is in about all genes of the cells, and activates transcription. And now HIF, here, hypoxia inducible factor, is in the heart of cellular functions, okay? So it does, in fact, it governs all these activities, just everything, growth, migration, angiogenesis, everything, metabolism, and if you look carefully, you can't see them, but if you would, you could probably pick your favorite protein out of all gene, out of this list, and HIF is in the heart. Taking this back to exosomes now, why are exosomes so sensitive to oxygen levels? Not a whole lot is known, okay, but we have identified two factors which are both from the family of RAB. So RAB22 and RAB20 have been shown to be key components of the very formation of exosomes. Obviously, you don't have exosomes if they don't form and go out of the cell. Now, what do you know? HIF here induces both RAB22 and RAB20. Okay, so effectively, what I'm saying here, I just showed you if you have high oxygen, like 21, like in an incubator, where whose cells are now at the incubator? Who has cells now growing in an incubator, CO2 incubator? Somebody has them, you just don't want to say it. If you do, what happened? You lose HIF, right? Which controls these which control exosome formation and secretion, and poof, it all disappears. Okay? So you do need low oxygen to stabilize HIF in order to have the exosomes. There must be something else to this story. For a fact, the RAB family, there's, GTP, everything. We don't know. That's your job. You guys have to go and figure this out. But this is quite convincing evidence out there in the literature already that we cannot make the mistake of growing cells in the wrong way. And just to show you, well, this is just a Western blot showing that HIF is truly degraded quite quickly, so you can't even take the cells out of the low oxygen for a little while, because you start the degradation process, which is irreversible. So only continuous hypoxia, physiological oxygen conditions, will guarantee that you don't have to worry about retracting the papers you're going to write about this. That's a nasty thing to have to do for a scientist. 10 years down the line, you have published something, and somebody goes and says, well, it ain't right, and you have to retract your papers. In fact, this happened to one of the Nobel Prize laureates in the photo that I showed you, to Greg Semenza. Unfortunately, he has to had to retract 4 of the key papers that brought him the Nobel Prize. They do not take the Nobel Prize away, so no worries for him, but it's a massive career mistake as a scientist to do things in the wrong way, and it will come back. It always comes back. Bringing things together, super promising therapeutic tools, the exosomes, they are, for diagnostic function as well. Keep in mind that where you get the exosomes, their function relies on the origin. The origin has to be good and kept in good shape. Like I said, they can only be fully utilized if they function, and if you have enough of them, that's one thing. They are, to an extent, way better than the cellular equivalent, which would be MSCs in this case. They function in a similar way, but they're just better to use because of the things mentioned. MSCs, like other stem cell types, always reside in low oxygen. Therefore, the conclusion must be that they have to be kept in their natural in vivo-like state. The question comes then, how do we do it? And I want to pick up this one paper where they actually used our Ruskinn workstation. They used to check and to produce exosomes. And if you want to go and check how they did it for protocol, please go and check this one. Lysyl oxidase activity, function, and exosomes was studied in hypoxic endothelial cells. But if you want to check for protocols, this would be a good one to go. Just to take that together, how to do it. This is how it's done. How it's done in the wrong way, by the way. Again, isolation and then expansion and they might precondition things, and isolation, purification, and then used in the therapy. This is how it's traditionally done. This means practically, this is what you would do in a lab. Then you have your exosomes from your stem cells. You put them in an incubator, and then you keep them there because it's nice and cozy and warm. Then you work with them in a BSC, right? Everybody does this, and then you maybe whatever, you inject them into the patient. Now, this is what's happened. Now, unfortunately, this whole thing is not what you should do here. What we propose is that you have your material, you have products where you can keep them in low oxygen from the get-go, okay? From the operating theater, if it's the umbilical cords, from that point on, put them in low oxygen. We can do this. Okay, there are ways to doing this. So straight from when the baby is born, you take your umbilical cord, put that in low oxygen, the same as the body would be, which in that case would be around 1.5, I assume. Take that into a ascites like you guys have here. Put them in there, same condition, low oxygen. Work in there. If you transport them to the patient, keep them that vial, wherever you have it in low oxygen, and then inject. So this is the safe way, and this is actually the only way to do it in a way that to avoid the things that I just described. Okay, it's not as easy, obviously, as what we're used to, but please take note. And if anybody wants to have any of these slides, you totally can. You don't have to worry about that. So this is the workflow, if you may. This is how it's then correctly done. So effectively, what we say here is that this is the same slide you already saw. This whole procedure goes into one of these. Now you have a site dual that's 1-2 boxes, but instead you can expand and you can actually add one more here. You can do the whole process. You don't actually need even a clean room. So imagine if you didn't have to gown up to go into a clean room. Just quite a lot of nicer thing to do. You could actually do the whole procedure here. You don't need your incubators or anything anymore. You just, this is the whole procedure, and from the end point, this is where they go into the patient. Okay, no gowning up, no building those very expensive clean rooms, no worrying about the corners that always collect dust. Just terrible. So this would be the solution, and that's how it looks in practice. And if you put it in perspective of a size of a human being, that's actually in Denmark, where we have a very nice unit in work. So just saying, too much oxygen is way too much. There are very serious consequences in the cells. That produces reactive oxygen species, also methylation events that I didn't touch, which is super important. We have shown that high oxygen causes changes actually in chromatin methylation, which is amazing because that's DNA level damage, right? Or changes. And oxidation of lipids and other biomolecules and enzyme inactivation and all sorts of things, causing cell death potentially. Why I say, or adaptation, which is even worse, it is even worse. If your cells die, you see that something's wrong. However, the cells that we get usually we get cells from ATCC or whatever, if they are just like regular cell types, cell lines, they grow fine. You know, stem cells grow fine actually in 21% of oxygen. The thing is that if they grow, it doesn't say that they are actually feeling good or they can still be used. They have adapted, and that's actually worse because that's kind of fooling us, thinking everything is okay. We have nice cells, they grow fast. Their doubling time is like 24 hours, but when you think about it, no cell in the body, most of them don't double in 24 hours. So that's kind of an artifact of us feeding them oxygen, sugars, the media that we give them, like that's a diabetic person, really it is. So just keep in mind that too much oxygen is really too much. Which is the shifting from, open culture where the cell stress curve, cells are stressed, so they just, feel all sorts of things. We propose these closed culture technologies where cells are very happy and solid all the time. And this box here was used for the Nobel Prize. Explain later if somebody wants to hear how that happened. So we can put anything in there, microscopes, and of course you can store your cells in there. There's a microscope in there for imaging, and that's how it works. You do the whole thing in here, and this would be your guaranteed production line for exosomes and therapies that follow. The last two slides, and this is the kind of a joke, but it's not, because I just want to emphasize that the work that Andrew has started with Ruskinn and then subsequently Baker Ruskinn has truly made a change in the field of science. Okay, and like I said, these guys won the Nobel Prize, and that's Sir Peter in the middle. So the thing that enabled him to do the work that he did, so of course that's life-changing for him, it's life-changing for science, and it's life-changing for him. So what Andrew's company and kind of us all together did was enable his work, and therefore we do have some very happy, loyal supporters, advocates for not only Hypoxia, but Hypoxia made by us, our company. And I just want to share this one fun slide that happened 2 weeks ago. So look at that face. Cute? Yeah? Cute? Good? Yeah? Look at that face. Okay. He got the Nobel Prize. 2 weeks ago, we did this, we have this Hypoxia EU community in Europe that we actually want to roll out here, but that's later. 2 weeks ago, we went to Dublin and we invited all the most notable hypoxia oxygen biology scientists to Dublin. Massively expensive city, by the way, not easy. And Sir Peter here was our keynote speaker because he likes the brand. He knows that Andrew enabled his Nobel Prize. And therefore, this very funny picture, can you see? See, this is the scientific thing that's being packed, and that guy, that Nobel Prize winner, here with Andrew, helping us pack after the show. So I think that kind of shows that, you know, we do have some happy customers. We do actually have these you know, help hands that come with the Nobel Prize. So I think that's quite entertaining. He actually volunteered to help us pack after the show. So we do form good relationships and do seriously help people with their science, and they seem to be very happy. So I leave it at that. I think I've spoken quite a long time, 49 minutes, I can tell because I have the clock here. And do you have any questions at this point?
Maybe I can ask one.
Yes.
Thanks this time, so very informative talks. But a lot of questions are turning in my mind. I just release one by one. The first one is about thanks for introducing the hypoxia.
Yes.
Yeah, that is new for us.
Okay, good.
And my first question would be that the normoxia is 21% in the outside. When we culture our stem cell in the tabulation and even in the vented flask, and what would be the percentage actually transpired or conveyed to the culture?
Yeah.
Is it 21%
yeah.
or less?
Yeah, that is an excellent question. Very good question. So there is no direct answer because the oxygen level that the cells actually see in the flask, so that depends on the media height that you use. It's probably, I don't know, 1 ml if you use 15 milliliters in 75 flask. So that affects. It also affects if you have any stirring, okay? So if you have just a standing, liquid layer, the oxygen does not go through. The answer, how you know, is that you measure. You do have probes that you can use. You can do calculations or estimation. You can measure actually from the bottom of the cell layer how much oxygen they have, and you can actually do intracellular measurements. But then also time, temperature affects how quickly oxygen dissolves into liquid. So it will be lower at times, but this is a good question because this introduces how difficult it is to do repetition, okay? Because the variables are, obvious, yeah.
Because usually for stem cell, it's usually the adherent cell, the bottom of that flask, whereby the diffusion of the oxygen will be much lower.
Yes.
My other question is about the hypoxia and
hypoxia. Yes.
Hypoxia. The physiological oxygen.
Yes.
The both will not degrade if 1 alpha, whereby that's why you can work with that what they call it can work with the DNAs and produce those factors. So based on your talk, it's more like the cell's defensive system against the oxidative stress which induced by the normoxia.
Yeah. So yeah, it is induced. However, at certain points and certain duration, it just overcomes the stress, overcomes the potential. Of course, we can use antioxidants, and they work to an extent. But then, if the stress is like 21% of oxygen, that's like quite high, and if that duration continues, it probably will be kind of like exhausted at some point. So,
Or what happens is the cells adapt to that new environment.
Yeah, they can, totally.
And survive the environments, but then they're adapted. So what happens when
Which is
you put
worse.
them back into the physiological environment is that's one step too
Yeah.
far.
Yeah.
They don't
Yeah.
work. That's-
Yeah.
And about, again, I have a few more questions.
Yeah, that's okay. Totally.
About, see, like I work with them for the past 1 years, okay? And we culture with normoxia. And recently, we are also using some natural products, and we found that the quality of the MSC can enhance. Now I could relate that is most probably antioxidant.
Yeah, probably antioxidant activity. Yeah.
And we our stem cell from the cord, bone marrow,
Yeah.
and adipose tissue.
Yeah.
And the oxygen level based on the origin,
Yes.
origin are different, right?
Yes, yes.
Let's say if I wanted to utilize adipose tissue MSC, and it require a different range of the physiological
Yes.
oxygen level,
Yes.
and it's compared to bone marrow,
Yes.
where it is more deeper in the
Yeah.
stem cell.
Yes, it is.
It's most probably 0.1%.
Yeah.
So in this case, do we have to determine the optimum oxygen level for different sources of the MSC?
Yes. Well, what you first do is you go through the literature and read a whole lot, because there are a lot of lists where you can go through and see what the optimal oxygen level would be. So I would do that first rather than go and test. But the boxes you can have in different, the ones that I showed you in the workstations, you can have one box in 1%, the next one in 5 or 2 or whatever. But you go through the literature, because lots has been done over the past 20 years. You can find sources, yeah.
Also based on your figure on the amount of that exosome produced. Although we saw that it has enhanced statistically the production, but when it comes to clinical situation, there is 2 points. One is statistical significance, other one is clinical significance. The amount of that exosome, I think it's one of your first figure you showed from one of the research paper.
Yes.
Yeah, although there is some statistical significance,
Yes.
but I don't think so that elevation will help patient in the clinic.
Yeah.
So how much for the hypoxia could provide when we are producing an exosome?
Yeah. Very good point. Well spotted. That is very true. It's not huge, but it probably can't be, because of, if it would be huge difference, then that would probably be not true, I'd say. But then even the small increase, obviously these studies, they have done them for like 48 hours or what have you. So if you do the whole procedure, and these haven't been done, procedure, that would probably give a little bit better still, but well noted.
Do you have any data on the using your facilities that you actually showing a few fold of the increase of the exosome?
Yes.
Compared to?
That
would be
there's a lot of papers, sufficient body of evidence is a good word. Yes.
And
but like I said, lots to do in this field.
And the other one is about the time trajectory. So in the control, that expression of the stem cell genes, salts, and
the
all
markers.
those things are
Yes.
actually increasing.
Yes.
Quite surprised to see that they increase as the 12 hours. But then, after 24 hours, you're showing a decline in the level of things.
Yes.
And maybe in 48 hours, it may normalize with the normoxia, right? So what is the significance? How do I interpret the data?
Yeah. So what happens if you keep kind of any type of cells, by the way? So I related that to the expression of HIF that is inducing the stem cell markers. Now HIF has this thing, depending on cell type, but we'll just generalize this. When you induce HIF gets increased in 6 hours or 9 hours or 12 hours. After about 3 days, depending on the cell type, HIF goes down, okay? And this has to do with the changes of activities in the cell. So what HIF actually does, and therefore what happens with the transcription or the stem cell markers, is that they kind of start to cascade, okay? And once that ball is rolling, so HIF has activated those, and now SARCs, NANOG, all of those KLS, they have downstream targets that then again get activated, okay? Or actually some of them get downregulated, true. But anyhow, so that's the cascade of events where HIF is no longer needed. And HIF does disappear in about 3 days after, depending on cell type. So therefore, the direct targets also start to decline. It doesn't say that the effect isn't still there, it's just kept the ball rolling, it's just moving them forward in their, however long the cells then live, obviously, so.
The gene expression of the stem cell marker were coupled with the protein expression.
Yes, they are in that paper actually. I can forward you the.
My last question.
Yes.
So you have shown that the quantity of the exosome are increasing. What the quality and the contents?
Yes. So both. So that is where the science kind of now stops at the production. So you get more. But there are good papers showing that the content is actually more similar to the origin of the exosome, the cellular origin or tissue, and also that the efficacy is increased. So the safety profile is the same; it doesn't affect that one. Of course, it's still pretty safe, but the efficacy would be increased. But that's where kind of the science, the front line of science is at this point, and therefore I kind of call you guys to help and see where that then takes.
Thank you so much.
Yes, thank you. If you have any other questions, we can talk now or we can talk later. And also, I have these cards, so if you want to ever email or call, that would totally. Of course.
I'm a clinician. I'm not a scientist. Do you think the effect of the hypoxia is direct on the exosomes, or is it as a result of its effect on the activity or pH of the environment?
So, like shown, there's few molecules that are known to be affected. It's probably the whole works. It has to be the acidity too, because it has been shown that even though the RAP increase of RAP 20 and 22 happened via HIF, they have shown that the HIF inducers, so there are molecules that induce HIF like DMOG and what have you, they don't do the same thing. So it actually has to be hypoxia, okay? So it has to be the oxygen, not the chemical equivalent of that. So it must be other things, but that has not been, it's not clear. It's not clear what the whole thing is.
Because as a clinician,
yes.
I'm not used to managing hypoxia when I deal with stem cells.
Yes.
But I've been taught that we have to look at the tissue pH very closely.
Yes.
And different from the blood pH.
Yeah.
And also, you have to correct me here, we are dealing with exosomes, therefore the cell, as different from the normal cells with the mitochondrials that depend on oxygen, aerobic and anaerobic
right. Yeah, they're just
different, right?
Yeah, well, they're not living things, they're just secreted bubbles also almost. They just have contents that have been wrapped in a lipid bilayer. So they don't have any of that stuff. Yeah, so that's different. Yes.
So the oxygen here is in relation to the exosomes only, not the whole cell.
No, it has to do with the whole cell. So the whole cell is experiencing low oxygen, okay, hypoxia, and therefore it can function. The whole cell. Now the exosome originates from the cell, from within the cell, which is low oxygen. Hence, the exosome too needs to feel low oxygen when it's secreted out of the system, out of the cell.
So you are working in an exosome in the context of a cellular environment, not exosomes on its own.
Well, not quite, not exosomes on their own, but they are just kind of like carriers of the message, because the cell pushes them out, and then they start seeking whatever target they know to somehow to go to. So that's just kind of a transport mechanism, and then they like the secreted proteins as well. So they're kind of like inactive and passive, you know, players in the whole cascade, where two cells, one here, the donor cell, if you may, and then you have the recipient cell here, and then the exosomes just, well, they don't float, but kind of like, in a way they do, and then they give the signal to the next cell. So yeah.
That is a question of how then you have the exosomes and how you deliver it to the patient.
Well, so we can do this. We can take the samples where you get stem cells. We can have those in low oxygen. The whole process into the lab, the whole thing that you need to process them can be done in physiologically relevant conditions. You can then put that, whatever product it's the injectables, into kind of a vial. Probably glass would be best, to be honest. Plastics is a bit bad. And then we can take that to the recipient. That can be done. It hasn't been done. You guys will be the first.
Because I'm now looking back at whether I'm doing the right thing or not, and we give the exosome transfusion.
Well, I mean, it's not the wrong thing, but you can just make it. You can just do it better. Yeah. You'll have happier patients. Yeah.
Last maybe for me. So since exosome is quite a simple structure.
Yes, it is.
And and when we know the profile of the exosome secreted by the stem cell on condition, can we easily synthesize them rather than use the MSC as stem cell as a resource to produce them? Can these not chemically or can be engineered and synthesized?
Probably. Nobody just does it yet, because they can be. But then. So, because it's not completely done, how the processing and the content, and not even only the content, the proportions of the content. So what we don't know, is it important to have like 40% of transcription factors and 20 of lipids, and is that important? We don't know. We don't quite know how the mechanism of the donor recipient tissue and cell go. So I guess that's the work that needs to be done. But for sure, that's where it's going to go, because you're going to skip the cell phase altogether, of course.
Because the molecules are very common for the Homo sapiens.
And they do have exosome depleted media. You know, you can use that. So that's the direction. The media companies wouldn't create exosome-free media if they weren't kind of like expecting that to happen. So,
What would be your recommendation? Because I have planned to start work on exosome.
Yes.
And what will be that right isolation way for the exosome?
What do you use now?
Now I've got using the filtration. The filters are commonly available. It's easy rather than ultra-centrifugation.
So just go with the kits. So they have a lot of these kits for exosome isolation. And they are good. I mean, they are as good as you have the filtration. Well, they are filtration anyways. But just make sure that you don't do it in a BSC, in your biological safety cabinet, because
even the slight changes during the process will alter that exosomes.
Well, that's the thing. If it does, then it's
You should find this exposure will change that HIF, right?
Yes, it will. It will be different. It will be different.
So in the case, even there's no point I'm having a CO2 incubator with a hypoxia, I need to have the entire package.
I know. Pretty, isn't it? I mean, but then you get the need for, you don't have to have a clean room. You don't have to do the governing up process. It was lovely, thank you. Lovely that you dressed me up yesterday. It was beautiful, nice experience, but you don't have to do that anymore. Clean rooms are pretty expensive, as everybody knows, to build them, and not massively effective, because even though they are clean rooms, they seem to be able to gather dust and stuff, and that's just the way it is. So yes, you're absolutely right. You shouldn't actually, to be honest, I shouldn't say that because we also sell incubators, but anyways, I'm saying you shouldn't have incubators. So there we go. There we have it. It's out. So yes, Dr. Pensman.
Thank you so much for the nice presentation as usual. So during my PhD, I was working at Hypoxic human science.
Yes.
So, and one thing I did by my own, because it was logic for me, because as Prof. just mentioned, the level of the oxygen in our culture dish and the flask, so normally because it's an aesthetic condition, it's not dynamic. So
No.
The resolved oxygen in the upper part of the culture medium come to the cell level may be different.
Yes.
So that's why sometimes maybe I don't know, maybe with the low RPM of the small shaker inside the incubator, we can let them to be more dynamic.
Yes. So if there's any convection, that would be great. Helps. But the guideline that I use, and I would advise other people to use as well, there are variables that we can't change. It's hard to say what it's just is, and people work in different ways, and there just are things that can change. So my suggestion and the way I used to work is just to, the ones that I can't control or change, I have to accept, but keep them constant. So if you don't know what the oxygen concentration on the cellular level in your flask is, let's accept that you don't know, but let's agree that you always use the exact same amount of media. So at least your every single experiment is the same. It's not perfect, but then experimentation never is perfect. So you just have to kind of, stabilize whatever you can, the variables that you have, just have them always constant, or at least try to make them constant. So the best that we can do, I suppose. So, yeah.
One of the challenges for me was culture medium was not to change the medium. Because at that time I haven't access to the isolator.
Yes.
It's a plastic in front of the hypoxic incubator. I put my hand inside the plastic, just a glove now we have. So how to, because I put the culture medium, the one I wanted to change the next day, 24 hours earlier, inside the flask, leaving inside the hypoxic incubator to absorb the soluble oxygen from the culture medium to change it. Because for me, bring from the fridge, put warm it and change it, it's become the reoxygenation.
Exactly, yes, you're absolutely right, it would be. So you need to take your media in the workstation in low oxygen at least 24 hours before, okay? Also the plastics, also your petri dishes or your 612 plates, because plastics is an oxygen sponge, and if you put that in low oxygen and you put cells in there, the oxygen is just going to be released from the plastics, and you're just going to, maybe it doesn't destroy anything, maybe it doesn't change anything, but then it might, and going back to then, or fast forward 10 years, and then you realize, oh, that was wrong, and just to be peace of mind, so that you know that every single experiment you did to the best of your ability. That's all we can do as scientists.